testing the V1 saliency hypothesis by a V1 model, part 3. For this hypothesis, we have built and calibrated a V1 model to resemble the real V1 on physiologically tested prototypical visual inputs. Now we can use this model to examine simulated V1 responses on other visual inputs to see whether the responses are consistent with human saliency behavior according to this hypothesis. Before we start, let's quickly see what we can expect from our model, which has such a bow tie pattern of neural connections. When there is an orientation singleton in a homogeneous background, this singleton escapes the iso-orientation suppression experienced by typical background bars, so it's the most salient in such an image. The iso-orientation suppression is achieved by having the disynaptic inhibition overwhelm the collinear facilitation. When we have a bar in a smooth contour, this bar could evoke a higher response than the typical background bar because the model has the collinear facilitation inspired by physiological data. When we have a texture border, this border bar is under collinear facilitation from above and below, and iso-orientation suppression from the right side. However, for a non-border bar, the suppression is additionally from the left side, making the response lower. This is analogous to the situation in any typical texture bar away from the texture border. As a first example, these two neighboring textures indeed evoke such a response pattern, with strongest responses to the texture border bars. Meanwhile, these border bars to the left do not evoke responses as strongly because each is suppressed both from above and from below, but collinear facilitated mainly or only from the left. These bars are more suppressed than usual since they have stronger neighbors from their left. These bars are slightly less suppressed since they have weaker neighbors to their left. These side effects of contextual influences can be manifested more apparently in later examples. Except when explicitly pointed out, all our plotted images are just small parts of larger images, extending beyond the outer boundaries. Otherwise, the texture bars near the outer boundaries will also evoke higher responses, just because there are fewer neighbors to give suppressions. Since the neural circuit is dynamic, the model responses actually change with time, so the plotted responses are actually temporal averages of the neural responses. Here is a plot of the responses across columns of textures with these column numbers 1, 2, 3, 4 as in the horizontal axis here, assuming that the model input appears at time 0. So these are response levels as function of columns at different time instances for each different curves. Initially at time t equal to 0.7, neural responses are indicated by this red curve, very weak and constant across columns. This is because visual inputs have not yet got enough time to activate the principal neurons sufficiently to make them effectively influence their neighbors. So each neural response is independent of the contextual inputs. So now with input contrasts constant across columns, the responses are also constant across columns. Slightly later, at time t equal to 0.9, neural responses have risen substantially across columns, and some variation across columns start to appear. At time t equal to 1.2, response levels reach a temporal peak. Interneurons are receiving strong drives from the principal neurons to become more activated. Strongest suppressions are in this column. At time t equal to 1.4, suppressions are stronger across columns. The suppression is weakest in these columns near the border. By time t equal to 1.8, most columns are completely suppressed except for columns near the border. So the excitatory drives to the interneurons are reduced or eliminated, so the suppression should also die down subsequently, and the next cycle of neural activations will follow. And this black curve indicates the temporal average of neural responses across these columns, and this temporal average is plotted in this response pattern. The temporal dynamics can be qualitatively understood as follows. First, the visual inputs drive the principal neurons. It takes a while before these neurons are sufficiently activated. Then they drive each other and the interneurons, including the interneurons for the neighbors. Some contextual influences should become evident. After the interneurons are charged up, this also takes a while, they exert suppressions. So contextual suppressions become evident. Once the principal neurons are suppressed, the interneurons lose their drives. Then their activations die down. So the suppressions should also decay away. Then the principal neurons will rebound or be recharged by visual inputs for the next cycle. Oscillatory neural responses are common for textured inputs to the V1 circuit. This is also observed physiologically. Typically, we only show the temporal averages of the model behavior, omitting the temporal dynamic details. As expected, when the input texture bars are left-right symmetric relative to the texture border, the responses are also symmetric, with highest responses still on the texture border bars. This makes the texture border salient, making texture segmentation easy. To better evaluate our model for saliency behavior, let's give a reasonable quantification of saliency values from the model responses. Recall from the V1 saliency hypothesis that the highest V1 response from each location is the bit for visual selection exogenously. So therefore, the model's bit at location I is this value bi. The average bit across location is denoted as b bar. The standard deviation of the bits across locations is sigma b, and we quantify the saliency at each location I by the z-score, defined like this. Accordingly, at this border location, the z-score is 4, and it's quite high, so this border pops out to attract attention. Here is another example. This is the input to the model and the model response pattern. And here is the saliency map, or the map of the bits from various locations. Here is a histogram of these bits. The highest bit comes from the location of the input cross, caused by the horizontal bar in the cross. It's an outlier bit with a z-score equal to 7, very salient. And this high z-score agrees with our subjective feeling that the location of this cross attracts our attention. Here are 3 input patterns. Each pattern is made of 2 neighboring textures with a vertical border between them. This border appears salient. The texture bars to the left and right are oriented minus and plus 45 degrees from the border, with a 90-degree orientation contrast across the border. This texture border appears slightly more salient. The bars are 45 and 15 degrees relative to the border, with a 30-degree orientation contrast. This texture border is not conspicuous. The bars are 60 and 45 degrees relative to the border, with a 15-degree orientation contrast. Such a small orientation contrast makes the border not salient. Spatial configurations also matter. This border is more salient because some bars are more parallel to the border. Similarly, this border is more salient than the example to its right because some texture bars are parallel to the border. So therefore, comparing these 4 examples, this border is the most salient. This one is the second most salient. This one is still quite salient, but this one is not salient. And this is how the V1 model responds to them. Indeed, the z-scores for the borders are agreeing with our psychological assessments of the relative saliencies of these 4 examples.